Hello, everyone, and welcome to Data Umbrella's webinar. I'm going to do a brief introduction about Data Umbrella. Then I will turn the camera and microphone over to Clair Sullivan, our speaker. And if you have any questions, you can ask in the chat or the Q&A tab. Please note that we will answer on-topic questions only related to this presentation and not outside of it. And we ask you to please respect that. This webinar is being recorded and will be available on YouTube within 24 hours. Data Umbrella is a community for underrepresented persons in data science. We are a nonprofit organization that is volunteer run. A little bit about me. I'm a statistician by training. You can find me on Twitter, LinkedIn, and GitHub at Reshama S. We have a code of conduct. We are dedicated to providing a harassment-free experience for everyone. We ask our attendees to behave professionally and be respectful, and we thank you for helping make this a welcoming, friendly community for all. There are various ways that you can support Data Umbrella. The first and foremost is to follow our code of conduct and contribute to making it a welcoming and collaborative space. Another way that you can support Data Umbrella is to join our Discord server, and you can ask and answer general questions there. You can share events and job postings and such. You can also donate to our nonprofit to cover our costs. We are on Open Collective as Data Umbrella. And as well, if you work for a company that uses Benevity, Benevity is a platform where your company will match donations made by employees, and we are on Benevity as well. We have a lot of video libraries on YouTube or playlists. One of them is contributing to open source. Another is career advice. And these are just some of the playlists that we have: data visualization, data science for beginners, scikit-learn Sprint, and we also have a series for the Python libraries, PyMC and NumPy. This is just a sampling of some of the webinars that we've done in the past couple of years. Our website has a number of resources available. Some of them include using inclusive language, allyship, accessibility, and responsibility, and we encourage you to check them out. We are on all social media platforms as Data Umbrella. The ones that are highlighted here, Twitter and LinkedIn, is where we share our events. Meetup is the place to join to find out about upcoming events. YouTube is where we post our webinars, and we as well have a blog and a newsletter. This webinar platform is Big Marker, and it offers live captioning. So if you go to the very top, there are two letters, CC for closed captioning. If you'd like to see live captioning at the bottom of your screen, you can select that option. For March, we're doing a special series of events to celebrate Women's History Month. This is the third in the series. It is arrays, linked lists, and graphs, and we have a couple more coming up. Next Tuesday, there's one for setting up a Jekyll blog using GitHub Pages, and the Tuesday after that is Intro to HoloViz for data visualizations, creating dashboards. Today's talk is Arrays, Linked Lists, and Graphs, Identifying the Right Tool for the Job. Our speaker is Dr. Clair Sullivan, who is currently a data science advocate at Neo4j, working to expand the community of data scientists and machine learning engineers using graphs to solve challenging problems. She received her doctorate degree in nuclear engineering from the University of Michigan in 2002. After that, she worked in a variety of research positions within the U.S. National Laboratory and federal government, and as a professor at the University of Illinois at Urbana-Champaign. In 2017, she accepted a job at GitHub as a machine learning engineer, and in 2021, she joined Neo4j as a data science advocate. She has authored 4 book chapters, over 20 peer-reviewed papers, and more than 30 conference papers. You can find Clair Sullivan on Twitter as CJLovesData1 and on GitHub as CJ2001, and she is on LinkedIn as well. And with that, I am going to turn over the camera and microphone to Clair.
Thank you. Okay, so good morning, good afternoon, good evening, wherever you might be dialing in from. My name is Clair Sullivan, and I'm just going to give you a warning straight up front that my internet service provider is not doing a great job today. So probably I'm going to turn my camera off here in a minute and just go off of audio, particularly when we get to the slides and whatnot. But I just want to thank you for having me here. Thank you, Reshama, for inviting me. And we're going to talk about something today that is kind of near and dear to my heart, which is connected data. And so I'm just going to dive in. Let me turn off my camera and start sharing my screen now. Okay, so let's get straight to the slides. Now, I would like to ask, we have the Q&A window in chat. So I'm going to try to be checking in on it somewhat regularly. And if you have questions, put them there. I'm going to try to answer them in real time, but my focus might be more on the slides, which is a different screen for me. So just bear with me. Okay, so arrays, linked lists, and graphs, and why connecting your data might make sense. Okay, so we're going to talk about some pretty basic concepts today, and then I'm going to introduce you to hopefully something that is going to be new and exciting to you. Now, we're going to be going through code today. And I am going to be putting this up on the screen many times. And it's also in the pinned comment on chat. And this is the repository. The repository has all of the slides and all of the code that we're going to do today. And I've got a lot to go through. We're probably not going to be able to get through all of the code, but I'll point out those things that, you know, those of you who would like to get into a little bit more depth, you might find some of those things useful. Okay, so what are we going to do today? First, we're going to talk about arrays, just data structures. We're getting into data structures here. Arrays, very common. We use them with great regularity in data science, as well as lists, which are a special example of an array. But then we're going to talk about a data structure that we may or may not be using with some regularity, linked lists. And there are two types of linked lists, singly linked and doubly linked. We're going to focus more on singly linked. Those are kind of the basic data linked list structures. And then we're going to get to a point where we're going to find that these things fail. There's going to be reasons that we want to get out of linked lists. So I'll talk about a new data structure. It's not really new, but it's perhaps new to us that can help solve these problems, namely graphs. Okay, let's dive right in. Here's an array, just a simple array. Okay, and what really happens when you create an array? Well, you've put some data into memory. So here I have my array shown on the right, and I've got memory addresses associated with these things. And what you notice here is that when you create an array, you've created something that has consecutive memory addresses. So as I go through those elements in my array, it's all of those addresses are linked. And this can be really fast. Using arrays can be really fast because we're not needing to jump around to different memory locations. We got them all consecutively. But the question is, what happens when we want to insert a new element into our array? Okay, so in this case, I want to insert this value of 238 between 42 and 186. Okay, how does that physically happen? Well, first off, what we're going to do is we're going to start copying elements. So this element 186, its element 2 is going to get copied to element 3. Sorry, I didn't use zero indexing there. Element 3 gets copied to element 4, and so on through the entire array. And then we insert 238 into the empty slot. Well, that's not very efficient. In fact, if you were to talk about big O on that one, that's a big O of n. So you can imagine as my array size gets large, this can be costly, right? Okay, like I said, big O of n. Now, let's say you're talking about lists, and all lists are dynamic arrays. Okay, we specify this empty list and we start putting our values into it. As you can see, I've put 3 values into my list. Now, when you create that list, what's happening is there's a certain fixed amount of memory that is pre-allocated for that empty list. And you can see that shown here by the non-shaded cells. Okay, so in this case, I just used an example of 5 pre-allocated slots. Okay, so let's talk about insertion with a list. It works the same way as an array because, you know, it basically is an array. But what you see here is I'm trying to, again, insert that value of 238 in there. And we can start copying down our elements all the way down the cells. Okay, so it might look something like that. And then I've got my slot that I can put 238 into, and life is good. But again, this is an order n operation, as we might expect, but there's going to be a problem here. So what happens if I've already filled my pre-allocated memory slots as shown here, and then I try to insert 238? Well, here's what's going to have to happen. First, we're going to do that element swapping like we did before, but you can see 1001 winds up in a bad place. So what has to happen is we have to allocate new memory to accommodate that growing list beyond the pre-allocated memory. And so that allocation of memory takes time. And then I still have to copy my elements from the old memory into the new memory. Those might not be consecutive slots. So this can be really, really slow. Okay, there must be a better way, right? And it turns out there is. Let's introduce the concept of a singly linked list. Okay, there's a few things. Let me see if I can get my little laser pointer to work here. Maybe not. Turn on laser pointer. Okay, here we go. So we're first going to introduce this concept of a node. And, we can think of a node similar to an entry within our array, but nodes have a few things. They have a data value, okay, in this case 42, and then they have a pointer. Everything when we're talking about linked lists is about pointers to memory. Now, those of you who come from a C background, pointers are going to be, native to you. You're going to understand this a lot better. I haven't actually programmed in C since the 90s, so I had to go get myself a reminder of pointers. And so each element in my list has that value and a pointer, and that pointer goes to the next node in my list. Now you see this red thing up here, 0x00200. What this is doing is it's pointing to the head. We call this first node the head of the list. And this red value here is the memory address of that head. Now, when I point to the next node, here's the memory address of that node. But check it out. I have the link to my next node here. Okay, and that's just a pointer pointing to the next memory slot. They're not consecutive. They don't have to be consecutive. And that's, as you're going to see, a really useful thing, a really cool thing. Now, we can keep moving. I've got, 4 nodes in here, and then I have my 5th node. That is my last node. The 5th node will point to null. Okay, that's how we understand that this is the last node in our list. Okay, now, link traversal, order n. Accessing elements by value, order n, because what happens is, unlike an array I can specify I want the second element in my array, but what we don't have consecutive memory here, so we kind of have to traverse through the entire linked list to find that one value that we're looking for. Okay, so why care? Why bother? Well, list insertion here is really super easy because all I'm going to do is I'm going to change the pointer here for my first node. Going back, you can see that my pointer pointed to this next node here. Okay, now if I fast forward here, I can see I just changed this pointer. I created my new node here, and it got assigned to that memory address. And then all I do is I set that pointer to my second node. Okay, so when we're talking about the insertion or deletion of elements, this can be an order of 1 type event. If you're inserting at the beginning, it's definitely order 1. Okay, if you're inserting at the end, it's order of n, because like I said, you have to traverse through this list. So when we're going to go to some code here, let's just go to some code and we can see this. Okay, so this is where you're going to want to go to the repository. And as a reminder, the repository is CJ2000, this is on GitHub, CJ2001/data_umbrella_linked_lists. And let's just take a look at this so you can see what's in here. Excuse me. Okay, I have my just a little README here. We're going to be using some notebooks today. It doesn't really matter what type of notebook you use, Jupyter or Google Colab, or you could use the VS Code notebook environment. I'm going to use Colab today just because it's fairly easy to get to. And it's also nice to be able, you can bring in GitHub notebooks pretty easily. When we start getting to graphs, I am going to be using some free databases. We're going to be using a graph database today, Neo4j. And these, you can get free database instances. They're called sandboxes. So it's just a nice, convenient, and free way to try things out. So we're also going to be using a few Python packages, pandas, which hopefully y'all have seen pandas before. And then because we're going to be connecting to a Neo4j database, we're going to be using the Python driver, the official Python driver for that. I want to call out some of the links here as well. This O'Reilly Graph Algorithms book, really great book, but I will tell you it's getting pretty deprecated and it's no longer going to be available. So if you want that, go get it ASAP. Got some docs here. Cypher, we'll talk about Cypher in a bit. Cypher is the query language for one of the most popular query languages for graph databases. Got some links to the drivers. I'm going to be talking briefly about something called the Graph Data Science Library. And what that is, it's a plugin for Neo4j that allows you to do some pretty sophisticated data science. And then the last thing is a video series that I've created called Bite-Sized Neo4j for Data Scientists. And my goal with this video series is to provide once a week a video that's 5 minutes or less. Sometimes they get to 6 minutes. I apologize. But every week I put out a new video, and it's just this small snippet focusing on one specific task in Neo4j. And I'll try to point out some of the more beneficial ones as we get there. Okay, for those who are going to code along, what we're going to do, I'm in Colab here. And one of the reasons I like Colab, like I said, is that I can go just grab things directly from GitHub. So I'm going to click Open Notebook. Okay, and GitHub, what you would have to enter here would be the name of the repository. Okay, I'm just going to copy and paste that in for the sake of time. Okay, so I'm just going to copy in this value. Now, again, this is as one of the pinned chat items. Okay, and I'll show it also many times within the slides. Okay, so let's give that a go. Okay, so it's going and it's grabbing the repository. And of course, it grabbed the wrong one. All right. That's great. Data umbrella linked lists. Okay, cool. And I'm going to open this basic linked list notebook. Okay, and so I've got the pre-populated notebook here. Now, if you don't want to follow along, that's totally cool, because if you scroll down, what you'll find out is I actually have included the outputs so you can see what's supposed to happen here. Okay, when we create a linked list, there's no data structure built into Python called a linked list. So we actually have to create that. And we're going to, in this notebook, we're going to create that through a few classes. The first class that we're going to create is this idea of a node. Okay, so we're going to tell Python that we've got this class called a node, and it's going to have a few values to it. You only really have to have like 2 values, but I'm going to include 3 just for this demonstration. We have the head, right? And that head is the memory location of the first node. And that gets allocated when I create this node. I have the value. So remember, I had those numerics like 42 and 186. So that gets stored in value. And then I have this concept of next. And next is that pointer to the next node. When we start off our linked list, you'll notice that it starts at none. And that's just because we don't have any of those pointers to start with. Okay, now the second class that we have is just the linked list. Okay, and the linked list class, right now, I'm giving it two methods. First is just the initialization of my linked list. And then second, I've got a print function here just so we can see what's happening. It's not necessary. So let's give these things a run. Yeah, I know it wasn't authored by Google. Run it anyway. Okay. Cool. And let's run this one. Now, here's what we're going to do is that we're going to create our instance called linked list, and we're going to add some nodes to it. First off, I'm going to tell it that the head of the linked list is a node, and I'm going to call that node Mon for Monday. Okay, I'm going to create a second node called Tuesday and a third node called Wednesday. Okay, now here's what I'm going to do. Remember, I had that next method. I'm going to say that the next node to my head is called node 2. Okay, in this case, Tuesday. So my head is Monday. My next node is Tuesday. Okay, now I've got my node next after that is node 3. Okay, so we're using this next method to populate our linked list in some sort of rapid fashion. Okay, and when I run that, I get Monday, Tuesday, and Wednesday. So that's my linked list. Okay, cool. Now let's make this a little more complicated. Okay, so I'm creating a new class that I'm calling linked list 2. It's very sophisticated and original. Okay, so I have, again, my initialization of my print statement, but let's create something that inserts a new node at the beginning. And remember, this is the order 1 thing that we were talking about earlier. So I'm going to create a new node, okay, and it's going to have some sort of data that I've passed into this method. And I've got the head. So the head is, remember, that first node, the memory location of the first node in my linked list. Okay, and then I'm going to change my head to be my new node. Okay, so we're going to run this, get my new class in here. Let's see what happens. Okay, I've created an instance of my new linked list. And again, I'm populating it the same way as I did before with Monday and Tuesday and Wednesday. Okay, but then here I'm going to go insert at beginning, and I'm going to insert Sunday. Okay, so you can probably guess what's about to happen. Okay, I've got Sunday, Monday, Tuesday, and Wednesday. Awesome. Okay, let's get a little more complicated now. Okay, so I've got my linked list 3 here, and I am now going to add a new method called insert at end. Now, you remember we have to traverse all the way to that end. So this is, this is order n, but I've got my data here. Okay, and I'm going to say if my linked list is empty, this is a nice catch function here or catch statement, then I'm just going to create my head node. But what we're going to do is we're going to iterate through my list now with this iteration variable here. Okay, so I start at head. And while I still have variables, you remember the last node in my linked list points to null or none for Python. Okay, so while it's not none, I am going to just say my iteration is going to go to the next node within the list. Okay, because remember we have that concept of next. Now, eventually I'm going to get to the place where it is null, and then I'm just going to add my new data here. Okay, and it's going to point at none because it's the end of the list, right? So we're going to give that a run. And then we are going to do the same thing we did before. We've got Sunday through Wednesday. Okay, I'm going to just keep creating next nodes, and I'm going to insert Thursday at the end and print it out. Okay, so you can probably guess what's going to happen here. Sunday, Monday, Tuesday, Wednesday, Thursday. Good. Okay, now at the next level, getting a little more complicated. Okay, so we've got insert at beginning, insert at end. Now we're going to insert in between. Okay, so basically, you remember we were trying to insert the value of 238 in between the values of 42 and 186. This is how we're going to do it. We're going to set our middle node, which we're going to put our value of 238 after that middle node. So in the old example, that would be 42. Okay, and then we have our data, what we're going to insert next, and that was 238. So if middle node is none, i.e. that is not in the graph, okay, then the mentioned node is absent. But my new node is we're creating that node, and it's being given the value of data, and it's being put in the position of next to my middle node. So middle node next is my new node, and I return. Okay. So you can imagine what's going to happen here. And I'm going to create my new node. I'm going to insert in between at node 3. What was node 3? Okay, so after Tuesday, okay, that's my node 3. I'm going to say, I wish it was Friday. Okay, which is true. It's Tuesday. I wish it was Friday. Okay, so here we go. Sunday, Monday, Tuesday. I wish it was Friday. Wednesday, Thursday. Okay, so you can probably guess what's about to happen next is I want it to be Friday. I personally want to delete Wednesday and Thursday. So we're going to add a new method here called delete node. Okay. if head value, okay, so this is just a catch that if I have nothing in my linked list, then we return. If my head value is not none, I can say if my head value is remove node. Okay, so that means that if my node is the very beginning, then I'm going to change my pointer here. Self.head is head value.next. Okay, so I've removed that beginning value and pointed now the head value is the next value. One of the things that this brings up here, everything that we're doing with linked lists is we're manipulating pointers, and we're manipulating them through this idea of next. Now, when you do that, it's kind of a key, and I'm going to show this in our next example. It's kind of important that you don't lose what those pointers are as you delete nodes. Okay, and I'm going to show that. We're going to do a LeetCode problem here in a minute. So just keep that in mind as we're going through this. Okay, so here's what happens if my node to be deleted is not my head value. So I actually have a head value. If my head value is equal to my remove node, great. But now I'm going to have this thing called previous. My previous is my head value. This is how I'm maintaining my pointers. Okay, so previous is what maintains that pointer to my head value. And then again, I just change that pointer. Head value equals head value.next. And then I can say previous equals next. Previous next is that head value next. Head value equals none. So you can run through this. Takes a little bit of thinking about what's happening with the pointers along the way. So if it's a little confusing right now, take some time after this workshop and just go through the code. I spent time sitting down just writing out, here's what's happening with this node. Here's which pointer is where when. Okay, so we've run that. So here's what I'm going to do. I've got my linked list now, and it's got all of my days of the week. Well, not Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, and Friday. Okay, now I've created the list itself, populating those nodes in there, and I am going to insert, I wish it was Friday, like we did before, and I'll print out the list, and I'll separate what's going to happen next by these lines here. Okay, now I am going to say delete Wednesday and delete Thursday, and I'm going to print out my list so you can see the difference between what happens here. Okay, so here's what we had before, Sunday, Monday, Tuesday, I wish it was Friday. Okay, but now I've deleted Wednesday and Thursday. I kept I wish it was Friday, and my wish came true. It is Friday. Okay, so that's just some really basic linked list stuff. Go through the code on your own. Hopefully it makes sense. Let's come back here. Okay, so we've just gone through that. Now, I mentioned before that there was this concept of a doubly linked list. Excuse me, let me grab some water. Okay, everything that we did before with our linked list was moving through the forward direction, and we were using that idea of next. We can use an idea also of previous. And what previous does, if you think about it, we only had on our singly linked list, we had our value and we had the memory location, the pointer to the memory location of the next node. But there's no reason we can't have another pointer here that points to the previous node. Okay, so for instance, this 375 points forward to 414 with that memory address, but it also points backwards to my 186. We're not going to spend too much time on this just because we don't have a lot of time in this workshop, but you can play around with this on your own. Okay. All right. So when might you use a linked list versus an array? Well, arrays are, like I said, they're really good at certain things. They're really fast at certain things. One of the things they're really fast at is if you know where that which exact portion of the array you're looking for. So like if I can say the index, like I'm looking for the third value of my array, that's super fast. That's order of 1. If you are expecting to be only deleting elements or inserting elements at the very end, then that's and you're not going to go beyond the allocated memory. Remember, the lists are dynamic arrays and they allocate a certain amount of memory. So as long as you're not going past that allocated amount of memory, an insertion or a deletion at the end is order of 1. However, linked lists are good when you just need a fast, easy insertion of data in general. So that's order one. And then the other time that you might consider using a linked list is when you don't have any idea how much memory you're going to need, and there's no real requirement on it being consecutive. So if you don't want to worry about how much memory is going to get pre-allocated, use a linked list. Okay, cool. Like I said, what you need to implement the linked list, we had these two classes. We had a node class, and that node class holds the data itself. And that data can be integers or, some sort of numbers like floats, or complex objects. So the things that you need here are the data and this idea of next. And if you have a doubly linked list, you have to have previous as well. And that's all that has to happen in the node class. The linked list class is the thing that actually holds those pointers to the next element. And so in order for that to happen, you need the head variable, which is the pointer to that first node. After that, you're off to the races. Okay. Let's solve a problem here. This is a LeetCode problem. So for those of you who are preparing for interviews, this is a pretty straightforward problem. I think it's in the easy category, but it's asked by a lot of different interviewing companies. So it's good to have this one in your back pocket. Given the head of a singly linked list, reverse the list and return the reverse list. Okay, now you see I've highlighted singly linked list. This would be trivial if this was a doubly linked list, but we can't have it be that easy, can we? Okay, so we have some examples here on the right. This is straight copy off of LeetCode. So LeetCode provides the linked list. So in this case, I see 1, 2, 3, 4, 5. And then the output they want is 5, 4, 3, 2, 1. Here's another one, 1 to 2 becomes 2 to 1. And then if it's empty, these are always the catch things that they always nail me on, is if it's an empty list. So we always have to be prepared for it being an empty list. Now, if you actually go do the problem, there are two ways to solve this problem, iteratively or recursively. I'm only going to do the iterative one just because we are limited to time. I leave it as a challenge to the attendee to go try the recursive solution as well. Just two different ways of looking at the same problem. Okay, we're going to use the code here in a minute. If you go into the repo, and we'll go in there in a second, there's the notebooks subfolder for the repo, and there's something in there called LeetCode206.ipynotebook. And that's what we're going to use here in a second. But let's just try and visualize what's about to happen here. Okay, first off, I'm just going to do 3 nodes here. We have our head. Okay, and our head has a value. We're going to give this a variable name called cur for current. Okay, and then we know that for heads, there is nothing pointing into it. So there's a null pointer into it. And I'm going to call that previous node the clever name of prev for previous. And then we know we have that concept of next, which sets up a pointer to my next node. And I'm going to give that a value of temp. Okay, so this is a temporary value. And you remember before I said that we want to make sure that we're not losing those links as we start messing around with our linked list. And that's what this temp value is going to do, is it's going to hold that memory location of the next node. Okay, so that's what's happening here. Oh, and here's our last node. And you remember the pointer value of the last node always points to null. Okay, cool. Now, the first step, we're going to actually break the link between 1 and 2 here, because I need to reset my value of my pointer value from 1 to null. Okay, so I need to get rid of this pointer value. But again, you remember that I need to save what this memory value is. I'm going to need it. It's just not yet. Okay, so the first thing that we're going to do is we're going to set this, we're going to set next of 1. Okay, so next of 1 should point to here. And we're going to set it to a temporary value to get the next pointer. And then what we're going to do is we're going to reverse the pointer. So 2 should then point to 1, or 1 points to null. Okay, and then I'm going to increment my current and my previous. Okay, and in this case, the previous points to null, and I'm going to have my current point to previous. just like that. Okay, so then here's what's going to happen is I've moved my temporary value. Okay, so it stores that memory address of 3, and then I'm going to make 3 point to 2. Okay, let's do that. Okay, so oh, I haven't drawn my arrow here. It's coming. And I increment again, current and previous. So this is why it's the iterative approach, is it marches down the length of my linked list and just iteratively resets those pointers. Okay, so current will eventually point to previous. I've set my temp value here. I note that the temp value is equal to null, so I know I'm at the end. Now, the important thing to realize here is that as we're doing this, previous is becoming the new head. Okay, so if I can point to the memory value of previous, then previous points to 2, 2 points to 1, 1 points to null. Okay, and that's how we're going to reverse all of this. Okay, so I think, yeah. Here we go. We're going to go into that notebook. And just as a reminder, the repository address, it's also provided within the pinned note in chat. Okay, so let's go. We're back in Colab, and I'm going to open that notebook now. Okay, and this is called LeetCode 206. Now, yeah, I don't need to save that. Okay. I remind you that LeetCode is providing the linked list itself. So we're going to do this a little differently in terms of classes. They have already implemented nodes and they've already implemented linked lists. And this is just copied straight out of their explanation again. Okay, so I'm going to have this list node class. Again, I've got a value and I've got a next to it. Yes, I know I'm not Google. Okay, so now we've got our list nodes, and now we're going to just have a function here, not a class, that's going to reverse our lists. Okay, so what we're going to do, we're going to start off with my previous variable equal to none, because you remember, let me just pop back to the slides really quick. Okay, so previous value started as null here, and current started as my head. Okay, so that's what's shown here. So while we have a current value, we are setting our temporary. The temp, that's the thing that holds that variable temporarily to get the next pointer. So always do that before you start breaking links here. Always save your next link someplace in the event that you need it again. Okay, so then what's happening here is I'm setting my next value. My current next is the previous. Okay, and that's what happened before when I wanted, let's see, I wanted current to point at the previous node. Okay, so here now I'm just playing these games with pointers. Next is pointing at previous. Okay, and then here's where I'm incrementing, I'm shifting everything. Okay, so previous is pointing at current. Okay, so that's shifting previous to the right. Current is pointing to temp, so that shifted it to the right. Cool. And then when it's all said and done, you remember I said that previous was my head. Okay, so I'm just going to return previous. And that's returning the pointer to that new head value. Okay, so here we're going to go. And this, I'm just using this to print off my values so you can see what's happening. Okay. So here I have my linked list. I'm just creating nodes 1, 2, 3, 4, and 5. And that's what's in the first example for LeetCode. Okay, and then I'm running this reverse list function on my head. So I'm just passing in the memory location of that first node. Okay, and here I see we've reversed the list, 5, 4, 3, 2, 1. Okay, so like I said, there's also, this was the iterative approach. There's also a recursive approach. Go give that a try. There's plenty of videos online on YouTube for how you can set these things up, how you can solve this one. Okay, so let's go back to our slides. All right, and like I said before, if we had been allowed to do that as a doubly linked list, this would have been trivial, but that's why they do it that way, is they don't want it to be trivial. Okay, now what if? What if this is the type of thing that you want to have? We've got all kinds of different things happening here. We've got singly linked things, and they're pointing back and forth in some cases. This is a mess, right? How would you implement this as a linked list? So maybe you see here, for example, node 2 points at two different nodes, 3 and 4. Maybe you could get clever and try to create a list of pointers for node 2 for the next pointer. There is so much of an easier way to do this than doing that. So that's what I would like to introduce to you now, the concept of a graph. Okay, so graphs, all they are, they're a collection of nodes and relationships. Sometimes those relationships are called edges. Sometimes nodes are called vertices. I didn't put that in there. But that's all it is. So it's a much cleaner data structure than a linked list would be for that previous image here. Okay, nodes, they have these things called labels. So in this case, I might say that this node 1 is of type yes?
Just a quick question. You have 2 5s there. Is that intended, or was one
Oops.
6?
Nope. One of them was supposed to be a 6.
Okay.
Let's say that one was supposed to be a 6. Good catch. Thank you. Okay. So, let's say node 1 is a customer, and the customer might have a relationship with node 2 called customer 1 emails customer 2. So emails, and customer 2 might purchase node 4, which could be an item. So the idea here is that nodes can have multiple labels or just a single label, and they can have properties such as customer 1 might have the name of Reshama, customer 2 might have the name of Claire. They can have multiple properties. Claire lives in Colorado. Relationships can have labels. So like I said, emailed or purchased, and those relationships can have properties. Maybe it's Reshama emailed Claire and 5 times. Another property would be those emails happened on these dates. So the graphs can have multiple nodes and relationship types. That's one of the things to take away. And again, it's a collection of nodes and relationships. That's all it is. How do you get graphs into Python? Well, there's a few different ways. There are some simple ways. There's some Python packages out there, open source Python packages. NetworkX is a pretty common one. You'll see a lot of NetworkX examples out there. And those are great. They don't require a lot of overhead in terms of database management because they're just Python packages. And they're also easy to query directly from Python because, they're just pip installable Python packages. But one of the problems is that there's not a huge amount of nice complicated graph queries that we can do with those things. Also, they don't scale real well. So, think about if you had millions of nodes and tens of millions of relationships, that's going to take up a bit of memory. And then you still want to do some calculations or queries on top of that. So when you get to that point, you want to think about graph databases. And hopefully by the end of today, I will motivate you to realize that graph databases really aren't that hard. They really, especially if you're using some sort of hosted solution like sandboxes, that infrastructure complexity can be managed for you. Neo4j is going to be releasing a fully managed data science database. It exists right now in Google Cloud. That's coming soon, very soon, to a theater near you. So then, like SQL, graph databases have their own query language. You remember I mentioned Cypher earlier. In case you haven't noticed, we kind of have a thing going with the matrix. The company is Neo. Cypher was one of the characters. There's also another thing in there called APOC. Yeah, we like our matrix. But it's similar to SQL. I'm going to show you some Cypher here in a minute. It's still, though, there's a little bit of a learning curve to it, but I promise you that it's not that bad. It's scalable. These graph databases, you tell it how much memory you want. You can have multiple cores. It's all good, whatever you want. And then the biggest thing is that these are set up for some heavy compute and complicated queries. And I'll walk you through what some of those look like here shortly. Okay. Oh, and they also have built-in data science and machine learning tasks. So if you go look around the internet, I've given a few talks and some blog posts about when using machine learning on graphs is actually better than just using it on columnar data, relationship data. If you know there's relationships between your individual points, you definitely want to be analyzing things in a graph space. Okay, so now I want to introduce you to where you can get those free database instances. This link here, sandbox.neo4j.com, this will set you up with a free database, and we have several of them that are pre-populated. Okay, let me show you this one really quick. Actually, let me start here. I've just created a few databases. One of them is called Graph Data Science, and it has a pre-populated graph of Game of Thrones. Now, I'll tell you, don't worry if you don't know Game of Thrones, because at the end of the month, we're releasing a new version of Graph Data Science, or GDS, and we're updating the graph to be something that's a little more timeless. We'll be using things like airport routes. So don't worry about this right now, but I'm just going to show you here. I am going to just take a look at this graph, and this is just some very basic Cypher. Now, what you will notice, we do a lot of ASCII art when we do Cypher. So when I have round parentheses here, that means nodes. And I'll show you something in a minute that is square parentheses, and that means relationships. Okay, so let's look at our graph here. This is going to create a visualization of Game of Thrones. Let me pop this out here, zoom out a fair bit. So you can see I've got a graph. Think about how complicated it would be to make this as a linked list. Okay, my nodes are colored with different labels, battles and people and houses, and some of my nodes have multiple labels, like I'm not going to give anything away and show you which people are dead, because that's part of the fun of Game of Thrones. Okay, I'm going to close this right now, though, because the visualization can take up a fair bit of memory within your browser. So I can get a quick visualization of what my nodes are and my relationships are. Here's all my relationships. I got a bunch. So that's cool. Let's see, let me come back to my slides. Okay, that's just another picture of it. So let's look at, we're going to just create a really simple graph, and I'm going to do that in a blank sandbox here. Now, if you look at the repository, let me show you where to find this. There's this subdirectory called Cypher queries. Okay, and I've got what's called basic graph.cql. CQL is a typical extension for a Cypher query. Okay, and all I'm going to do is I'm going to create some nodes, and I'm going to create some relationships. Okay, so I'm going to create a node. See that round parentheses there. Now my next thing here, this is a variable. So I'm going to give that node the variable name of x1. Okay, now this here, target, this is my label. This is my node label here, target. Okay, and then when I use curly braces, this means a property. So I'm going to give my node a property called name, and its name is going to be x1. And I'm going to do this, I'm going to create just like 9 or 10 nodes here, 10 or 12 nodes, I can't count. I'm going to create, I have another type of node here that I'm going to call source, and it's also going to have a name. So I create my nodes this way. Now I'm going to create some relationships too. I'm going to create a relationship between N1. Remember, that's my variable name from up here. Here's N1. I'm going to say N1 connects. Now, this is our format for looking at a relationship, is those square brackets. And we also use the colon here to denote a relationship. And so N1 is going to connect to X1. Now, check this out. I've got these lines here. This is a little arch for arrows. So N1 is connecting into X1. Okay, and I'm going to do that for a whole bunch of relationships here. If you want, you can spin up a blank sandbox instance. All you do is copy and paste this in there. You'll get a graph. Okay, so I've already pre-populated this just to save time. So I'm going to match n. This is kind of like select star and return it in SQL, if you're familiar with SQL. Okay, so here is the graph that we just created, and I can play little games here where I move these things around, and it makes it easier to visualize as I move my nodes around. Okay, so that's just simple. You can go play with this, and there's all kinds of courses online where you can learn Cypher. It takes a little. It's not that hard. Okay, it just takes a little effort on your part. Okay, so I'm going to open a new notebook now, and we're going to be querying my that linked or the Game of Thrones graph. So I am going to be looking for where is it? I'm looking for GOT queries. Of course, it's going to be difficult to find. It's coming up with all of my. Let's go back to our repository here. Here we go. Okay, actually, I'm going to go to this graph data science one here. Yeah, I know. Okay. Now, here's the thing, is that if you are running this on Colab, you have to tell it to install the Neo4j driver package. If you're doing this on your local machine, you can just pip install this from your command line or whatever. Let's just go get it. Almost done. All right, cool. So we're going to use pandas, and then we're going to use this graph database concept from Neo4j. Okay, now this is a class that I've created that creates the connection to the database. If you're interested, I have some of those bite-sized Neo4j videos on this. There's the bite-sized series is about 28 videos now, and I'm adding one every week. If you look at part one, though, part one is how to make the connection between Jupyter and one of these sandbox instances. And then part four is how you can do some basic queries, and it specifically shows it within Colab. So let me just give this a run. All right, cool. I have a concept here called closing, and I have my initiation, and I've got a query here, so I can run my queries with this. Don't worry about this for now. Okay, now we need to make a connection to my sandbox instance. And in order to do that, I'm going to go back to my UI here. And I'm going to click this little drop down here. And you can see I've got these tabs here. I'm going to click on connection details. Now, here's the important thing is I have the URL to my actual instance, and this is happening through the Bolt protocol. The Bolt protocol works on port 7687. So let me copy that to my clipboard, and I'm going to drop it in my URI right here. Okay, and then I need my password. My password is right here, lifts feeder input. There are always these three-word things separated by dashes. Okay, so let me come back to here, and I'm going to drop my password in. Okay, now I'm going to establish my connection, and I'm just going to query it really quick. Okay, oh, my username is always Neo4j. Okay, so here is my Cypher query that I'm going to use to do this. Match n, return count n as count. So what I'm saying here is match all of my nodes and return the count of them and assign it to a column name called count. Okay, so this looks a lot like SQL. So I'm going to present these results in a few different ways. One of them is just what the default return value is, and then I'm going to give it to us in a little bit more usable fashion. Give it a run. Okay, so I have 2,642 nodes. Now, if I come back here, that should agree with my total number of nodes, which it does, 2,642. So that's good. Okay, coming back into Python. All right, I mentioned this thing called the Graph Data Science Library, or GDS. It's a pretty sophisticated set of things, and I'm going to just do one very brief demonstration with it. I am going to try and calculate PageRank on this Game of Thrones graph. Now, for those of you unfamiliar with PageRank, this is an algorithm that was famously developed by Larry Page at Google. It was pretty much the first iteration of Google, where they tried to estimate the importance of every node within a graph. And their graph in this case was the internet, the whole internet, which web pages link to which other web pages. Now, PageRank, the higher the PageRank, the more important the node within the graph. Okay, but it's not even just based on the number of links, but the quality of links. Like, for example, let's say the New York Times had a link directly to my GitHub account. Okay, New York Times is a pretty influential webpage, right? So, and the fact that that influential webpage was linking directly to me, that's a pretty special thing, right? It's all about who you know. So that would increase the page rank of my GitHub page. Okay, so there's a few steps that you have to do in order to run GDS on anything. The first is we have to create this thing called a graph projection. And what that is, it's an in-memory thing. It's a pretty memory efficient way of representing what we care about in the graph. It's not going to be something that's easy once you've created it. You're not going to interact with it directly too much. You're going to use it to run graph algorithms on it. In this case, we're going to run PageRank on it. Now you'll see here, I've got a whole bunch of links that show you, here's how to get to the just information on GDS and the API docs. And here's the specific, this is a Wikipedia article if you're interested in how PageRank is specifically calculated. Okay. Now we're going to call this function, again, here's my Cypher query. And it's called GDS graph create. Now I'm going to give you a heads up that when GDS 2 comes out at the end of this month, this syntax changes a bit. It's not going to be called graph create. It's going to be called graph project. But for the sake of what we're seeing here, the rest of it looks the same. You just replace create with project. Okay, so I'm going to run this. And basically what we're doing is we're creating an in-memory graph called people. And I'm going to take all of the nodes of label person. Okay, so if I go back here, I can see that I have a node label somewhere in here. It's this kind of teal thing called person. Okay, and so I have to query nodes and then I have to query relationships. So as you might imagine, I'm going to take all of my person nodes and I'm going to look at every single relationship type that they must have. Okay, ignore that query error. Failed. Why did it fail? This is one of the great things about LeetCode. Oh, I already created it. It's already in there. So that's what that means. I had not deleted the graph yet. So if I try to create a graph with the same name, then it throws me this error. That's fine. We already know that it's there. Okay, now here's what I'm going to do. I'm going to create a new query. It's going to be called a PageRank query. Okay, and this is just a string, just like I had, strings up here. So what I'm going to do is that I'm going to call PageRank, which is a built-in algorithm to GDS. And then I have this thing called write, and write writes those page results back to each of my nodes. I'm going to run it on this in-memory graph called people, and I'm going to write a node property back called PageRank. Okay, so then I'm going to run this query. Okay, so it's done it. Now let's just look at what it looks like. Okay, so I have PageRank for every single person within my graph. So here's what I'm going to do is I'm going to match my node of person. Okay, I'm giving it the variable of P. So for every node, it's kind of like a for loop. This person is going to have this PageRank and that person's going to have that PageRank. I'm going to return a couple things. And these are properties. This is how we specify node properties. So my nodes have a property called name, and we know because we just created it, they have a property called PageRank. So I'm going to return that, and I'm going to order it based on descending PageRank. Okay, that kind of looks similar to SQL. I'm going to limit it to 10, very similar to SQL. And what I'm going to do is I'm going to output this in a data frame, a pandas data frame. And this is just some nice syntax for getting all of those results back in a data frame. I'm going to look at the top 10. Okay, so here they are. So I've got my names, I've got my page ranks. And if you happen to know Game of Thrones, this is not surprising, these first few entries. But then there's some names down here that we don't necessarily recognize. This is based on the books, by the way, not the TV show. And it's looking at which characters co-occur with which other characters in the same scene. So I don't actually know who Yandria and Ysilla are, and I was a pretty big Game of Thrones fan. But what this suggests is that these characters, they were interacting with important characters like, say, Tyrion Lannister. Okay, so Tyrion Lannister, pretty important character in Game of Thrones, and these people interacted with important people, so that's why their page rank is so high. Okay, so it could be that we've just done this as every single relationship type, and it's some of these characters, like I said, they're not important to the story. So we're going to create a new in-memory graph, and we're going to limit it to the relationship of interacts _1. And what the _1 means is just that they're interacting in the first book only. There's all kinds we could choose other, we could look at who's attacking whom or anything like that. But that's what we're going to do. Is same idea. We've created that in-memory graph. We're going to write PageRank in this case. We're going to use this new in-memory graph called people _1, and we're going to write out PageRank _1. Okay, so we're going to do those queries, the projection query and the PageRank query. And then we're going to just return the results just like we did before. Okay, so yeah. It said that I already have a graph named person1. Sorry about that. I'd already run it, but now we have our results here. And we can see that in the first season, our interactions are happening between characters that are, most of them are pretty well known within that season or that particular book. I don't know who Willis is here. But these are some pretty important characters. So that's what's happening in this notebook. I encourage you, if this is something that you're interested in, there's tons and tons of different graph algorithms built into GDS, calculate all kinds of things. Centrality, meaning node importance, clusters, meaning who is grouping together with whom. There's link prediction as a machine learning thing. There's all kinds of stuff here. Now, I've gotten a question. I apologize that the question windows are just on a different screen. If you have Neo4j on a non-networked machine, how do you point to your database? So that's a great question. And this is coming from SM McCarthy. If you go into my my repository, just my personal stuff, I've got all kinds of examples of that. I frequently run Neo4j locally. And let me just pull up some repositories that you might be interested in. There's I believe we show that in the bite-sized series at some point here. Basically, what you're going to be doing there, you're not going to be using the Bolt protocol. You're going to be using a different protocol, and all you're going to do is you're going to start up Neo4j, and it will open itself up on port 7474. You can't quite see it there, but 7474. You could then just point your web browser at localhost :7474, and you can have this browser window directly on the screen. You can also run, like if you're running Jupyter locally, then instead of, let me come back here, scroll up a touch. Okay. When we make that connection, instead of using Bolt and then this IP address ending in 7687, we're going to replace this with Bolt localhost. So anytime you're making a Bolt connection and doing this from Python is where that's going to happen. You're going to point at 7687, and it will ask you to provide a password for your Neo4j user when you first start it up. So you'll just put that password in there. I hope that answers your question. Okay, let's go back to our slides now. We're winding down a bit. Okay, so let's just do a quick recap. Okay, to recap, we know arrays and lists are limited by insertion problems, which can be an order n event. And linked lists are beneficial because the insertion is order 1 and you don't need to pre-allocate memory, which, as we recall, was a big problem when we were dealing with lists, which pre-allocate memory. If you go past on your insertion, if you go past that amount of pre-allocated memory, that is slow. Okay, and then we talked about what happens as those network of nodes becomes more complicated, and then you want to think about moving to a graph data structure. We can do that in Python. We can do that in a graph database. And I hope that I can kind of help you get a leg up. Which is that, yes, you can do that in Python through something like NetworkX, but eventually as you get into graphs, you're going to want to scale, and NetworkX and other Python packages, and there's a few of them out there, they're not going to scale as well if you're doing this all in memory. You want to go to a database solution, just like you wouldn't want to stay in pandas forever. You're going to, if you have columnar data, you're going to eventually want to go to a database like a SQL style system. So just think about starting in a graph database to begin with. It's going to save you time in the long run, just because of that scalability, and also because there's a lot of built-in algorithms that are much more computationally efficient done on the database rather than locally. Okay, just another reminder of where the repository is, and the slides are in this repository. This is where we've been getting all of the code today. And I just want to say thank you. Thank you for coming. Reshama, thank you for the invite. Please reach out to me on Twitter if you have questions. You can reach out to me on LinkedIn too. But I love interacting with people, and I love talking graphs, among other things. So yeah, I guess I'm going to end this there. I'm going to stop my screen share, and I will turn the camera back on. Let's see if my network wants to cooperate with me. So thanks. If you have questions, please throw them into the Q&A portion of chat, and I'm going to stick around for a few and see what questions happen to come in. So thank you.
Claire, thanks so much for this presentation. I know there's been a lot of interest out there about learning about linked lists. So thank you so much for explaining it, particularly with Python as well. Yeah. So,
Definitely.
yeah, I'm curious to, I'm actually I'm a Neo4j certified developer. I went through the course and I passed the exam. And so, thank you. Do you have maybe a starting point for people who might be interested in Neo4j?
Absolutely. We host on the webpage. If you go to neo4j.com, you're going to look for this thing called Graph Academy. And what Graph Academy is it's a whole bunch of courses out there. We're updating them constantly. We have some new ones coming out on the new version of GDS. But Graph Academy is YouTube videos and associated content with it where you can go learn graphs. The other place is by going into sandbox.neo4j.com, where you can create these free sandbox instances. There are several of them. You can look through. This movie's one. This is really where everybody learns. But there's leaks. This is into who's illegally sending money where. Twitter, you can create a graph of your own Twitter now. What's that?
Your sound went off in the last sentence. Just to let you know, if you want to repeat it, if you want to try to repeat it.
Sure. Sandbox.neo4j.com has a whole bunch of pre-populated databases. Everybody starts off with this movies one that is Cypher based. I'm going to just turn off my screen here just so we don't have that happen right now. We've got the ICIJ offshore leaks, which is looking it's data journalism, and it's looking at who is shipping money to which offshore places. You can create a graph of your own Twitter network. There's all kinds of pre-developed things in here. Some of them you can see are specifically tagged for data scientists. But one of the great things in here, I'm going to come back this is the Game of Thrones set. The GDS and movies graphs in particular, they have these things called browser guides. And what they do is they walk you through step by step what's happening in the graph. It shows you all of these different Cypher queries that are used, how to look at things, statistics on things, and then it shows you how to do.
Claire, are you able to share your screen if you're?
Oh geez, I'm sorry, I did not hit that button. So sorry. Okay. My bad. Okay, sandbox.neo4j.com. So just you can see now, hopefully, all of these different graphs that show up in here, and these will pre-populate for you, so you don't have to worry about importing your own data. There are blank ones in here too if you do want to import your own data. But then looking at that, this is that browser guide that I was talking to you about, and you can just scroll through, and it lets you run these queries. So I just click on it, and hit run, and I can see what happens. It's a great way to learn Cypher in particular and how to interact with GDS. So between Graph Academy and Sandbox with these browser guides, I would say those are the two most useful ways of quickly coming up to speed.
Great. So we'll stay online for a couple of minutes and see, if people have questions. The video will be available soon. I will also write up a blog on this because it helps to have both a blog and a video to see, where people are interested. There's a lot of really, really good, valuable information in this presentation. So I will be watching it again this weekend. Yeah, folks, so if you have any questions, now is the time to ask. I see there's one in the Q&A if you want to read it.
Okay. For DSA, Python is not widely used, but I mostly code in Python. So do you have any suggestions for somebody who wants to start learning DSA in Python? I will be honest, this is coming from, I apologize if I mispronounce this, DSA is not an acronym that I'm familiar with. I am about to Google it. Yes, and if you Google it, you're not going to always find what you're looking for. Can you post? Embarrassing that I don't know this. Okay. Digital signature algorithm. Is that what you're referring to? Is digital signature algorithm, digital storage architecture, digital signal analyze?
It says data structures and algorithms.
Data structures and algorithms. Okay. So now where did the question go? Okay. So if I recall correctly, the question was, do I have recommendations for DSAs with linked lists? Is that data structures and algorithms? Thank you. Okay. So getting started with data structures and algorithms, do I have recommendations there? So there is this book. Hang on, let me grab the title. It's perhaps my favorite book on DSA, data structures and algorithms. It's on my Kindle right here. Let's see. What is the name of this book? Hello. Yes. Okay. So it's called Data Structures and Algorithms in Python, and it is by Basant Agarwal, and of course the title screen just went away. But look for that book, Data Structures and Algorithms in Python by Agarwal. It is available on Amazon. Okay, who has other questions?
So I think we're at a good point to end. Thank you so much, Claire, and thank you so much, and we'll be in touch. Okay.
Great. Thanks, everyone.
Okay. Bye.